Good morning, everybody. Happy Monday. We hit that magical negative 40 degrees with the wind chill number, and that equals a cold day. If you didn't know that, by the way, that's kind of it's maybe an unknown secret about cold days at schools, but they cancel when it gets declared as a wind chill warning, and negative 40 is the cutoff for wind chill warning. So this morning we hit the magical number. The National Weather Service declared it as a wind chill warning, and here we are. Anyway, that has nothing to do with what we're learning today. Today, let's jump through 6.7. This is on bond enthalpies. Again, that word enthalpy is just a fancy word for heat or energy. Okay. The only time that enthalpy and heat are not the same thing is when we have some work being done. But like I said previously, none of these problems are going to be doing any work. Okay. So, and when I use the word work, I'm obviously talking about, the physics definition of work. But anyway, so no work being done, enthalpy equals heat. All right, so today we're going to look at bond enthalpies, and this is one of the more fun things in this unit. I really like today. This is kind of a fun, mathy, little, straightforward, easy situation. So I hope you like it too. All right, couple intro things before we jump into our very first problem, and this is really important. The important part here is obviously the bolded text, but let me run through this. So when chemical reactions occur, the chemical bonds of reactant molecules are broken. Chemical bonds of product molecules are formed. Makes perfect sense, right? We need to break down what we previously had and create what the product needs to be. Breaking bonds or attractive forces requires energy. Okay, now this, and sorry, the opposite of that, right? Making new bonds or attractive forces releases energy. This is everything. This is everything in this unit. This is like the biggest takeaway that you should have all unit long. Don't mind my box. There we go. Off the screen. I much prefer a smartboard. Oh, well. Okay, this, highlight it, underline it, everything. Just draw some attention to it. I know I've already bolded it, but I want more attention drawn to it. When you break bonds, okay, it requires energy. When you make bonds, it releases energy. This comes up again and again and again and again on the AP test. So please make sure you can do that, or you're confident in those two statements. Breaking bonds requires energy, endothermic. Making bonds releases energy, exothermic. All right, so if all of the bond energies of the reactants and the products are known, one can simply add up all the energy required to break all the reactants and add up all the energy released when the new ones are made. The sum of the reactant bonds is always a positive value, meaning that requires energy. The sum of the products is always a negative value. Add these two values together, and you have delta H, or the enthalpy, for the entire chemical reaction. Okay, so let's jump into our very first problem here. We have C2H6O, which I have given you the structure of. This is known as ethanol. And we have oxygen as the other reactant. Now, hydrocarbon, oxygen. What kind of reaction is this? It's combustion. We are burning something. Okay, whenever you see something with carbon and hydrogen, and the other reactant being O2 gas, this is something burning. All right, now, what are the products of combustion? We get CO2 and H2O. Okay, and again, don't mind my writing today. I'm using the little pen pad thing to make this happen. So pause it. Balance this if you could. That'd be great. I'll assume maybe you've tried. Maybe you're back now. I don't know. Anyway, but here we go. I need 2 of those, because I have 2 on the left-hand side. I need, let's see, 3 of these, because I have 6 hydrogens on each side now. My oxygens, I have 4, plus 3 more gives me 7. Got 1 right there that I can't mess with, so that means I need 6 more. And we should be good. All right, now, when we do these bond enthalpy problems, okay, you'll notice on the right-hand side here of your sheet, I've got this gigantic, this gigantic list of all these different bond enthalpies. This is from your periodic table from last year. If you flip to the back of last year's periodic table, this is right there. And what we need to do is add up all of the bonds over here for the reactants, put that as a positive value, add up all of the bonds over here as the products, and give that total as a negative value. When we break these bonds on the reactant side, it requires energy, endothermic, positive. When we create these new bonds on the product side, negative value, energy is released, exothermic. So let's get this organized. I gave you this first structure because that's kind of ridiculous, but we need the other structures of these three things, okay? So this is like unit 2 or 3. I forget when we were drawing Lewis diagrams. I think it was unit 3. But if I go right here, okay, you may remember that oxygen is doubly bonded. Carbon dioxide also has double bonds on either side of the carbon. And then, of course, water is just an oxygen in the middle and 2 singly bonded hydrogens on either side. Okay, we could go through the whole Lewis diagram stuff over again, and we will when we start reviewing for the test. I think it is a good idea to make sure you still know how to do that. But for the sake of time today, let's just kind of plow forward a smidge. All right, so let's get into this then. Oh, maybe. There it goes. I'll switch color. All right, so let's do the reactant side first. On the reactant side, I want to add up all of these bonds in both of the molecules and get the total amount of energy required to break them all. All right, so the first molecule, there's a lot going on, right? I have carbon-hydrogen bonds. 1, 2, 3, 4, 5 of those. I have carbon-carbon bond, just 1. I have a carbon-oxygen bond, just 1. And I have an oxygen-hydrogen bond, just 1. But I need to account for all of those, every single one of them, in order to get the math right here. Okay? If I go here, oxygen, O2, right? It's a double bond. Now, we count double bonds just once. I don't count each of those bonds individually. I go over to my chart, and if I scroll down, I can find O2. Hopefully you can see it. Okay, I can find O2, or sorry, yeah, a double bonded oxygen right down here, and it has its own separate value. So double bonds, triple bonds get counted once, and there's a value for that double or triple bond in the table. All right, so let's do this. Let's set it up. Now, I'm going to try to structure this the same way every time. I'm going to try to structure it where I have the number of the coefficient first. Okay, I want this coefficient as well. If this is a 2, I now have 2 of these molecules, right? And instead of having 1, 2, 3, 4, 5 carbon-hydrogen bonds, I would have 5 from one molecule and another 5 from the other for a total of 10. So the coefficient absolutely affects our math. It really, really matters. We must account for how many of those molecules we have. So I have one of this molecule. All right, sweet. Then let me use a coefficient of 1. I'll have the next parentheses be the number of that bond in my structure. So I have 1, 2, 3, 4, 5 carbon-hydrogen bonds. We're starting there. And then we go find C and H in our chart. It is 413 kilojoules per mole. Okay, I'm not going to use labels today. 1, because I'm using this pen thing and it's a pain. But 2, this is kilojoules per mole. This is moles. These two values, right? This is like the number of moles. I guess the coefficient is your moles. The moles thing will cancel out. So we're going to be left with just energy, which is what we're looking for. All right, that's my first term. I then add that to my next term. Now I just find another different bond on my reactant side and add that up too. What's another bond type? Carbon-carbon single. Okay, let's do that. Coefficient is 1. I have one of those bonds multiplied by CC single, 346. There we go, kind of. Okay, let's find another one. CO single. Coefficient is 1. I have one of those in that molecule. I find CO single bond, 358. Yikes, it's getting worse. Let's keep going. Plus OH single. I go and find that. Way up top, here it is. Oh, the order doesn't matter, by the way, right? Do you see how it's OH in our molecule, but this is HO? It's the same thing, right? Just ordered backwards. It doesn't really matter. Same elements. This is the one we want. 463. So I have coefficient of 1, one of those bonds, and my energy of that bond is 463. Okay. We have accounted for every single bond in this molecule. We have 5 of the CH bonds. That's this first term. We have 1 of the CC bond. That's the second term. 1 of the CO bond. 1 of the OH bond. Every single bond has been accounted for in this molecule. Remember, these are the energy required to break these bonds. When you break bonds, you got to put energy in. We have one more reactant that we still need to account for. Different molecule, but we need to account for the oxygen double bond here in the other reactant. So let's keep going. Plus coefficient of 3. Again, this means I have 3 of those molecules, right? So it's not just one double bond that I'm breaking. I must break 3 of the double bonds. How many of those bonds do I have? Just 1 in the molecule, right? So the coefficient is 3. Inside the molecule structure, I just have 1 double bond. I go find, oops, sorry about that. Oh no, I'm erasing stuff. Oh, that was a plus sign, okay. What number was that? But I go find oxygen. Way at the bottom of, right above my face, hopefully you can see it, O2 or O double bond is 498. All right, now this is the reactant side. Excellent. I'm going to set up a total. I want to get the total for the reactant side. Okay, before we do that though, hold on, I'm going to switch color. We'll do green and purple, I guess. That's kind of obnoxious, but oh well. Let's go to the product side. Let's get the products. We'll do the products in green. On the product side, I have these 2 structures. I have carbon dioxide and I have water. Let's add up all the bonds of these 2 molecules. I always start with the coefficient. I had a coefficient of 2 for my carbon dioxide, multiplied by how many CO double bonds do we have? 1, 2 in the molecule. So I have 2 times 2, multiplied by the bond energy of a CO double bond, which is 803. Really, really high. Plus, let's go to the next molecule. I have, oops, water. Coefficient of 3, 1, 2 OH bonds in that molecule. So my coefficient is 3. I have 2 of that bond type, and I have an OH bond is equal to, oops, I think I scrolled down too far, 463. And then I have the product total as well. So grab a calculator. Let's bust this out. Let's see how much reactant energy we have, how much product we have. I'll do the same. Okay, I've got a total of a positive 4,726 for the reactant side. And for the product side, let's see here. I've got a total of 5,990. Now, let's be a little careful. On the reactant side, this is energy required, endothermic. On the product side, this is energy released, exothermic. So I'm just going to take that and flip my sign at the very end. There are other ways to do this. There's other ways to account for the products being negative, but I honestly think the best way is just add everything up on both sides, get a total for the left, get a total for the right, keep the left side positive, flip the sign of the right side. It seems to be the most straightforward, the easiest to pull off, and the easiest to do. Now, what do? We have the enthalpy of the reaction is that plus this. So I have a positive 4,726 minus 5,990, and my total of the enthalpy of the reaction is a negative 1,264 joules. Or kilojoules, I'm sorry. Let's try that. Whee! This is getting ugly. I hope you can read it. I'm obviously verbalizing what I'm writing too, so let's see if it's more difficult than a normal day. I hope we're not failing, crashing, and burning here. Anyway, So that's our final answer. This is the process. That's it. Again, it's pretty straightforward. You got reactants, we got to break those. Takes energy, positive term. We got products, we're going to make those. Releases energy, negative term. I add up every little individual bond in every molecule, accounting for the coefficients. I add up every little individual bond, again, same way. Get my total over here, get my total over here, and smush them together, and we're good. Go ahead and try another one. I'd like you to pause it and try this, okay? Now, oh, actually, I'm sorry. Hold on, time out. Little mean. I gave you a bunch of words, but no structures, right? Yeah, the idea here is that you, in theory, know how to do Lewis diagrams still. It's been a while. But let's balance this out. I have H2 plus N2 producing NH3. This is not balanced. We should totally do that too. Okay? 2 of those. 3 of these. And I think we're good. Now, we need the structure of this stuff. Hydrogen gas is a lone little single bond between 2 hydrogens. Nitrogen gas is a triple bond. You may remember that, you may not. And ammonia has a nitrogen in the middle with 1, 2, 3 hydrogens all attached to the nitrogen, like such. And there's a lone pair if you care, or if you're curious. Let's, now pause it. Okay, now you got everything you need. Why don't you pause it now? I'm trying to make this work. There we go. Pause it, come on back, and let's do the reactants and the products for this reaction and see what we get for the overall enthalpy using the bond enthalpies. I sincerely hope you tried it. I have a hunch about 80% of you didn't. But if you did, welcome back. I appreciate your effort today. Coefficient is 3. I have 1 HH bond. I'm doing the reactant side, right? What's the total energy of an HH bond? 436. First one on the list. Plus, I go to my next molecule. Coefficient is 1. I have 1 triple bond. The triple bond energy for the nitrogen is, holy cripes, let's find it, way down there. Near the bottom. It's kind of tough to see on this sheet, but I promise you on your periodic table, maybe it's a little easier to see. We have a triple bond of nitrogen equal to 946. I hope you can find that. It's way near the bottom. That's it. Those are my reactants. I can get a total. Let me jump to the product side. Oh, why does it fight me? Stop. Just work. There we go. We'll go cool. Product side, I have a coefficient of 2. I have 1, 2, 3 NH bonds in that structure. I look up NH somewhere. Near the top, HN, it's listed backwards up there, but again, same elements, so that's exactly what we're looking for. 391. And that's it. Nice and short one. There we go. This one's a little happier. Let's get our totals. I have 3 times 1 times 436 plus 1 times 1 times 946. I'm getting a total of, let me switch color again. It's going to fight me. Yep, there we go. Oops. Getting a total of positive 2254 kilojoules. Let's go to the reactant side. 2 times 3 times 391, also known as 6 times 391. And I get 2,346 kilojoules. And again, we just flip the sign at the end here. So, we add them together. The overall enthalpy will be the positive 2254 plus the negative 2346. And we get a grand total of the enthalpy change of this reaction equaling negative 92 kilojoules. That's it. There's 2 more. Go through them. Again, I'd really like you to try this stuff. If you watch me, this isn't bad. Okay, I'm leaving you blank on some of these structures, but the idea there is that you should, in theory, try to do the Lewis diagram to get the correct structure. If you're feeling extra fancy on a cold day, you're welcome to try that too. But I'd like you to do the math. This one's got all your structures. Cl2 is a single bond, by the way. HCl is a single bond, so nothing fancy going on here. please try it if you could. Okay, let's try this again. I was having some technical difficulties. I don't know if you can tell on the video or not, but that's fine. Let me run through and set this up. I was trying to set up chlorine, chlorine single bond, and HCl, oops, single bond. Sorry for the hideousness of that. And I'd like you to try this if you have not. If you have tried it, excellent. But let me go through it, okay? If you haven't tried it, again, pause it. Please pause the video. I would love for you to try this because it's you know, meaningful for you to try these things and not just watch me click away and struggle to write legibly. Although I'm sure that's fun. All right, so let's do the reactant side. Okay, I have this molecule, which looks kind of complicated, but there's only two types of bonds. I've got some CH bonds, I've got some CC bonds. So I only need to do two little categories for it. We should be careful and make sure this is balanced, but it is. It is, just making sure. So I have a coefficient of 1. I have 1, 2, 3, 4, 5, 6, 7, 8 CH bonds. Ooh, yikes, sorry about that. Can I erase? I can erase. Nice. Okay, so we find CH, it is 413. Plus, I have two CC bonds. Coefficient is still 1, multiplied by 2, multiplied by CC, which is single bond 346. Ooh, yikes. That looks like a G. There we go. Maybe a little better. And then I have one more reactant molecule. I have chlorine-chlorine single bond. Again, coefficient is 1. I have one of those bonds in my structure. And now I gotta go searching for this thing. There it is, ClCl 243. Okay, sweet. This is my reactant side. I get a total. I'll do that in just a second. Let's go to the product side. We'll use red, that's fine. On the product side, we have a similar looking molecule. We still have, it looks like 1, 2, 3, 4, 5, 6, 7 CH bonds. Coefficient is 1. 7 bonds, and these are CH, so that's still 413, just like it was from the other side. I have plus 1 carbon-chlorine bond in there. Coefficient is 1. One of those, carbon-chlorine, about a third of the way down, 328. Plus, I have carbon-carbon bonds still. Coefficient is 1. 2 of those bonds, and it's 346, same as earlier as well. Okay, I have another product. I have HCl. Coefficient is 1. One of those bonds in that molecule multiplied by HCl, which is 432. And I have my product set up. Now it's just the math, so let's punch all this stuff in. So 1 times 8 times 413 plus 1 times 2 times 346 plus 243, because 1 times 1 doesn't do anything, obviously. And I get, for the reactant side, a total of, uh-oh. Oh no, come on, calculator. All right, we've resuscitated it. 4,239. Thought about taking this part out, but nah. Where's the fun in that? 7 times 413 plus 328 plus 2 times 346 plus 432. On the product side, I'm getting a negative, because again, we want to flip the sign. Oh, I'm sorry, I'm using blue. Let me use red, just for the sake of continuity. There we go. Negative 4343. and that's also kilojoules. For our total enthalpy, let me scroll down. We have an enthalpy equal to the 4239 minus the 4343. Rather, I should not say it that way. I'm adding those terms, right? So 4239 plus negative 4343, which gives me a grand total of negative 104 kilojoules of energy. And that is my final answer. So again, I hope they find this pretty easy. It is pretty easy, especially when you have all the data you need, right? You don't have to go digging for it in a book or something like that. We'll be digging in books tomorrow, which is a good thing. We're in the chem room. I'm going to have to bust out the AP Chem books finally this year. But for those of you at home, fear not. Obviously, you don't have a book. We'll make it work. Anyway, so we're good. Let's do one more. If you have not done this, please do this. There's some balancing to do. There's some drawing to do. Yeah, let me be nice on this one. This one's the weirdest Lewis diagram you would have ever tried. So let's balance this out. Nitrogen's good. Hydrogen, I've got 3. I've got 2. That's not great. Let's make this work. I've now switched to nitrogen, though, so let me just do that right away. Everything should be balanced except for oxygen. Let's take a peek. 2 times 2 is 4. Plus 3 more gives me a grand total of 7. That's not fun. Just making sure I didn't do it wrong. No, I didn't do it wrong. So I needed to 3.5 here, right? Which is going to change everything. 4, 7, 4, 4? Is that right? Who put this on here? This is rude. 4 of those, 4 of those. 12 of those. That's not right. Oh yeah, you know why? Because when you double 3, it's totally not 4. Oh man, this is falling apart. Let's try 6. 12 of those, 12 of those. And then we just got oxygen. Looks like we got 14. 4 times 2 is 8, plus 6 more is 14. Gotta be right. Alright, so, structures. N, 1, 2, 3, single bonds to hydrogen. And there is a lone pair there if you care. Oxygen, that's a double bonded molecule. This guy, if you really want to try it, go ahead. But I promise you, it's super annoying. We'll have 1 double bond, 1 single bond. If you want to get deeper into why or how or what, we can talk about that later. But yeah, I'm just going to streamline the process here on a at-home cold day. There are our structures. Let's set this up. If you haven't tried it, again, please try it. I'd like you to try it. Pause it and come on back. But let me go. Coefficient of this first one is 4, multiplied by 1, 2, 3 of those bond types, multiplied by NH bond, which is 391, plus coefficient of 7, multiplied by 1 double bond in that structure, multiplied by an OOO double bond, which is 498, near the bottom. I don't know if you actually, I don't think you actually saw it on my video, but again, if you have your sheet right next to you, you should be able to see it just fine. Oops, let's not do that. And this is going to equal something for the reactant side. Let's go to the products. We'll go with the purple and green combo again here. On the product side, I have a coefficient of 4 for that first molecule, multiplied by an NO single bond. I just have 1 of those. So let me look up NO single. There it is, 222. Plus coefficient of 4 multiplied by 1 for the NO double bond. An NO double bond is going to cost or be worth 607. Plus the other molecule, I have water. Coefficient is 6. Multiplied by 2 of those bonds in that structure, multiplied by OH or HO, which is up here, 463. And we get a grand total for both sides. Let's check it out. Hopefully my calculator's still hanging on here. 4 times 3 times 391 plus 7 times 498 for a grand total of quite a bit. I'm getting 8178. Oh, didn't switch color for me. kilojoules. Okay, on the reactant side, 4 times 222 plus 4 times 607 plus 12 times 4 times, or 6 times 2, right? 12 times 463 for a grand total of negative 8,872 kilojoules. It's for our grand total enthalpy of this reaction equaling a negative 694. Oops. All right, and I am all done. I hope that makes sense. Let me go through a couple of, housekeeping things. Homework topic 2 is due tomorrow night. Okay, we have done everything that you need to do. It has nothing to do with this sheet. So please work on homework topic 2 and be ready to turn that in by tomorrow. This week, we're going to finish this unit. We're going to do 6.8 tomorrow. I think we should be able to finish that in class tomorrow. We'll do 6.9 on Wednesday. We'll get close to finishing that in class on Wednesday. We might finish it. Thursday, we'll do an in-class review. Friday's dead because we have in-service, so you guys don't have to do anything for Friday. However, like a third of you did the lab from last week Friday, so, there's that. And next week, Monday, we're going to have a test. So, quick unit. I warned you it was going to be a quick unit. Yeah, very, very quick unit. We're going to finish the unit this week. We're going to have an in-class review on Thursday. We're going to test on Monday. So, there's plenty to do on Friday. I know it's not technically a school day for you guys, or I guess over the weekend you can do any of this stuff. I'll post all the answer keys. We'll do an in-class review on Thursday, and we'll be good to go on Unit 6, and we'll jump right into Unit 7, which, if you may have picked one up. They were downstairs for the pickup. If you came in, if you were a virtual student, I sincerely hope you grabbed that. If you're an A or a B kid, I guess I don't know what week it is. Whatever week it is this week, I'll give you your packet, right? And whatever week it is next week, I'll give you your packet next week if you haven't gotten one. So, just a side note. But anyway, have a lovely day. That's all I got. No need to check in for live class, obviously. You're watching the video. You're good to go. And we'll see you guys tomorrow. Thanks, guys.